be from Xuehai Chen to tell us about a system called DecoMine.
So I'm very happy to present our work on the graph mining system based on the pattern decomposition. And so here we provide the motivation for the graph processing. We know that the graph is a universal data structure that captures the relationship between many real-world applications. And also a recent issue in the communication of ACM, it also emphasized the importance of the graph data analytics. On the other side, we are in the new golden age of the computer architecture. So on one side, we have the high demand to support the AI and big data applications. And on the other side, we are facing the end of Moore's law and dynamic scaling. So the way and the viable path is to enable the vertical integration of application, domain-specific language and systems, architectures, and emerging technologies. So in this work, we propose the innovative ideas to close the gap between the algorithm and the system for the graph pattern mining. So in general, the graph processing system, so it looks like this. And normally we have a simple programming model so that the user can specify the operation on the vertices and the nearby edges. And then there is a runtime system here that handles the operation that is common in the system. For example, how do we handle the communication and the synchronization between machines? And you can also, optimize the runtime system for the different backends. So in recent years, we have studied the graph processing in the architecture domain and also in the system aspect. We focused on the graph computation, which is more traditional, and recently we look at the graph pattern mining. So we have 3 talks here, and but in this talk, we're trying to look at the gap between the algorithm and the system. So first, let me briefly introduce the concept of the graph mining. So for the graph mining, we have 2 inputs. One is the input graph that we want to mine and find the patterns, and the second one is the specification of the patterns. So the goal is to enumerate all the subgraphs of the input that are isomorphic to the given pattern. For example, in this case, we have the input graph here, and we have the pattern here, right? So here is 2 subgraphs that match the pattern, and they are called the embeddings. And so the graph mining has application in many real-world problems. So for this reason, in the system and database community, the researchers has built different kinds of systems over the years. In general, we have 2 methods. One is pattern. One method is called pattern oblivious. It means that we want to enumerate all the subgraphs up to a certain size and check whether it is a matching of the pattern. The other one is called pattern aware. Basically, we want to construct the embeddings based on the pattern. So what is the challenge of the graph mining? One of the challenge, I believe, is that there is still a big performance gap between the current system and the efficient algorithm. So here, you can see that we basically run different systems on a task, and then we compare the performance with efficient algorithm based on the pattern decomposition. You can see that the system performance is improving, but there is a large gap between the best system performance and the algorithm performance. So the goal of this work is to try to close that gap. And before that, we want to introduce what the computation of the graph mining looks like. So for example, in this case, we have an input graph, a pattern graph, and the embedding. So the pattern of the computation is essentially the nested loop. We want to start with every vertex in the graph, and we want to construct the embeddings by looking at the neighbors in a way that is specified by the pattern graph. So of course, what matters is how do you generate the code? For example, what is the order of So what is the order of the program that matches a different, so that matches a different vertices? So next, I want to introduce briefly about the pattern decomposition algorithm, and then present the challenge why we need to have the new ideas to support that in the system. So for the pattern decomposition, so the goal of the algorithm is to try to support the larger patterns. And the first step is to partition the pattern in a way so that the different so that the pattern is partitioned into subpatterns, and all the subpatterns so they share a vertex cutting set. And here you can see that the two subpatterns, they share 3 vertices, and it's an overlapping area. Right? And then you can try to match the pattern, smaller pattern of the, so you can match the smaller like, sub-patterns. Here is 2 examples of like the embeddings for the sub-patterns, right? And then you get the count of this, so you get the count of this embedding, and then you can see that you can conceptually perform the joint operation, and you can multiply M1 and M2, and you can get the whole, so the number of embeddings that match the full pattern containing these 3 vertices. But based on the selection, for example, you may select the same vertex for the 2 like embeddings. So maybe the combined and the joined like embedding is different from like the original pattern. So we need to also eliminate those cases. The original algorithm paper, so obviously a problem is how do we select the, so how do we decide the breakdown or the decomposition? So the algorithm paper, they try to analyze the algorithm for the specific pattern and try to understand that in terms of the computation complexity and upper bound, and then choose the implementation with lower upper bound. So it is not suitable for the general purpose graph mining system because we need to support arbitrary patterns. And our solution is to build a compiler that can generate the algorithm for different vertex cutting set and the general, so the compiler can generate the algorithm for different vertex cutting set and all the patterns. And also we use a cost model to select the best choice. But before we describe that part, we also need to solve a new problem. So what API can preserve the algorithm? So what API can preserve the advantage of the algorithm? So this can be explained in this example. Here we consider the application called frequent subgraph mining. So basically, the algorithm tries to find the frequent patterns from the graph. And here we need several, so we need to have like several definitions. The first one is the domain. Domain is a set of input vertices that a pattern vertex can be mapped, so a pattern vertex can be mapped to. So when you consider the different like embeddings, you can see that one pattern vertex can be mapped to the different. So one vertex in the pattern. So one vertex in the pattern graph can be mapped to the different vertices in the input graph. And then there is a measure called mini support. It is the size of the smallest domain across all the graph. So the size of the smallest domain across all the pattern vertices. So the FSM discovers the frequent. So it discovers the frequent like patterns by finding out the support with no less than a threshold. So the problem of, so the current graph mining system allows the user to define the user-defined function, and so basically the system can return embedding, and then the user can specify. So the user can specify like what do you want to do for the embedding, right? So there is an interface between the system and the application. So the problem here, when we adopt that method directly with the pattern decomposition, is that in this case, it means that the system needs to substantiate all the whole pattern. So all the embeddings of the whole pattern, which takes time and introduce overhead. It is not the same as just calculating the count. So it will like diminish the advantage of the pattern decomposition. So it will like diminish the advantage of the pattern decomposition algorithm. So our idea to solve this problem is to have the partial-embedding API. So the idea is that the system does not need to return the embedding for the whole pattern. And instead, the system can return the embedding to the user that matches the subgraph or the subpatterns, right? So for example, system can return this partial embedding, and if it does not match like a vertex in the if it does not match a vertex in the whole pattern graph, it is indicated as a star. So we found that this interface is sufficient as long as it satisfies two conditions. The first one is a complete condition, means that the system should be able to correctly return all the embeddings matching the subpattern. Second one is a coverage. It means that all the subpatterns should cover all the vertices in the pattern. And obviously, these two conditions can be satisfied by the pattern so these two conditions can be satisfied by the pattern decomposition algorithm. So, for example, in this case, the system will return the partial embedding, and then we can update the domain of the vertices in this partial embedding. But we do not need to update all. And we found that this interface so naturally fits the pattern decomposition algorithm. So next, this slide provides an overview of the compiler. So the compiler is able to generate the algorithm for the arbitrary patterns based on the flow of the algorithm, and it's based on the template here. And there are two parameters. One is the order that you match the vertices in the pattern graph. Another one is the selection of the vertex cutting set. So the next question is how does the compiler choose the best implementation? And here we need a cost model. Traditionally, or in the recent work, people use the probabilistic so people use a probabilistic analysis to estimate the cost. For example, here we assume that the graph is random and there is a probability of a connection between the vertices of the graph. And when you construct the pattern based on the distance of the different vertices, you may have the different number of the expected, so the number of the different expected connection. And this connection is reflected as estimation of the number of the iterations in each loop level here. And we found that this is not accurate. So the prediction is not good enough. We can slightly improve this method by introducing the locality, basically assigning higher probability if two vertices are closer to each other. It improves a little bit, but it's still not enough. What we proposed is approximation-based. So what we proposed is approximate mining-based cost model. So the central idea is to estimate the number of loop iterations at a level by the corresponding pattern reaching that level. So for example, here we have a pattern, and these are two possible implementation of the matching of the pattern, right? So you can see that we can have a different matching order. And if you want to estimate the cost for the third, so for the third loop level, you can see that the first implementation reached that by ABC, and ABC corresponds to a pattern 3 Chen. And this implementation reached this level by DBC, which is a triangle. So the idea is that we can somehow get the estimation of the Chen and triangle from the input graph and use that as a proxy to estimate the cost. But on the other side, we need to do that fast. So the idea is that based on the large input graph, we sample a fixed number of edges. And so here is a random sampling. And based on the smaller graph, we can also run the approximate mining. So we can also run the approximate mining algorithm to build the table here. And of course, the information in the table is relative and it's not accurate, right? But it satisfies our requirement because we only need to have this table to estimate the performance, and as long as the cost is comparable. And this figure shows that our prediction using this method is much more accurate than the previous method. And also the more accurate prediction of the performance translated to the performance improvement overall. So overall, the system looks like this. We have a compiler that will optimize and generate the code at intermediate level. based on the cost model. And when we select the best choice, we can generate the code, and the code can run in the real machine. So we compare the performance of our system with several recent systems. So for example, this table shows our system, DecoMine, compared with our own implementation of the AutoMine in SOSP19, RStream, and Arabesque. And you can see that the performance improvement is orders of magnitude. And of course, that is because of the better algorithm, but we need to have the system innovation to support that. This table shows the comparison of DecoMine with the Paragram, Pangolin, and Factorial. So again, we achieved a good speed up. Particularly, Pangolin is a system that can use the GPU, and we can see that our CPU-based system can have a similar performance as a GPU, but the cost is much cheaper, and also GPU has the limitation in the memory, so it cannot run like certain tasks. So this slide basically shows that our system can indeed close the gap between the performance of the system and native algorithm. And here we compare our performance with the Escape, which is a native algorithm for the pattern decomposition. It's optimized by the expert and for the specific patterns here, right? And with one thread, we found that our system, on average, is 4 times slower than that algorithm, and this is because we cannot apply some of the optimizations that are specific to this pattern. So the recent system, the best they can do is that the gap is 17 times, and this is also considering the fact that they are using the optimization that is only so they are using the optimization that is only that is only applicable for the pattern counting. But with multi-threaded, our system is better than the algorithm. The last slides indicate the performance on the large graph and large patterns. So on this side, it's a result of the large graph, and you can see that compared to the recent system, we can reduce the execution time from tens of hours to like less than 2 hours. On this side is large pattern. We can sometimes reduce the execution time from days to hours. Okay, so that is the end of end of my talk. So in general, our system is the first system that is based on the pattern decomposition, and it achieves a very good performance that is similar to the native algorithm.